All right, let's finish up chapter 4. Chapter 4 is more on logarithms and exponentials, but now we're using them in problem solving, which makes sense because that's what we do. We are a problem solving people. We'll get the pin first. I'm going to do 4.5 first. This is on equations with exponentials and logarithms. Sometimes we will take advantage of the following rule. X equals Y is the same thing as saying log base A of X equals log base A of Y. So it's kind of like it is like treating a logarithm as an operation. Just like multiplying both sides of a number by multiplying both sides by 3 or something like that, taking the logarithm of both sides. So how can we take advantage of this? Now, previously, what we would have done is said X equals log base 8 of 21. And if you have a calculator, you could do it that way. That uses that, or with the change of base formula, we could write that as log 21 over log 8. That was the old method of saying Y equals A to the X is the equivalent as X or Y equals log base A of X. Another way we can look at this is use the properties of logarithms and treat it like an operation. Remembering that log base A of A just cancels out, equals 1. So what we can do is use this base here to make a logarithm of the same base. And we're going to do it to both sides. The exponent rule pulls the X down. This becomes X times log base A of 8, which is 1, equals log base 8 of 21. Which is what we did here. And there's less thinking about this transition. I always have to stop and go, where does everything go when I switch from here to here? I have to pause and think about it. And I've been teaching this shit for a long time, doing it for a long time. So I imagine, unless you have just some like natural gift for logarithms and exponentials, you have to slow down when you do it too. But going, this is the same base, I'm just going to use both sides of the same base, and that just brings the exponent down. I can remember that as just a one-stop shop. That's a one operation. I don't have to think about it. Just use the bases there. This can be helpful in problems where it's not, we've got bases on different sides and it's like, well, what do we do? So check this madness out. All right, people are so bad. I mean, slow down.
Or you put the arrow, like.
Well, yeah, I'm saying this is the same thing as 1. Let me make that a different color. Log base 8 of 8 is 1. I do that a lot when I have, if I say like a to the 0, you'll see me do this. I'm kind of like saying, let's cross that out, even when I cancel fractions. If I have 5/5, I will cross things out like that and do that. Thank you for asking. All right, let's take a look at where it gets shiftier, where we can't even really use the exploits we've done here well. And taking the logarithm of both sides is definitely the way to go. What if we have something like 5 to the 2x minus 3 equals 8 to the x plus 1? I've got different bases on both sides. So like even swapping them in and out for like using the way we learned in previous chapters isn't going to help, because if I do it to one side, I got to do the other, but it's not going to help anything. So what can help is just taking the logarithm, take log or ln of both sides. I'll do logarithm or natural log, because I want you to get used to using both. Now we can use our exponent rule and bring down the 2x minus 3. And we can bring down the x plus 1. And it leaves ln of 5. And it leaves ln of 8. So these are like coefficients. These are just numbers. Just a value. If I put it into a calculator, it's just a value. Which means I can distribute it to everything. I can say 2 times natural log of 5 times x minus 3 times natural log of 5 equals natural log of 8 times x plus natural log of 8. What would I do if this was just like a 5x on the left and an 8x on the right? What operate if this was just 5x and this was just 8x? How would I solve this for x? What? I'd combine them by, I'd have to move one of them over by subtraction. Same principle, but now it's not 5 and not 8, it's these ugly things. But I can still do that same operation. So I can subtract natural log of 8 times x from both sides. And since I'm moving everything, all the x's to the left, I'm gonna move the other stuff to the right. Here I have 2 times the natural log of 5. X minus the natural log of 8. X equals 3 ln of 5 plus ln of 8. This is just some number in a calculator. We put it in a calculator, we're gonna get a number. Let's say it's like 0.6, something like that. So just because it's ugly as fuck doesn't mean it's not just a number. Now, I can't really combine these as is because they got different not natural logarithms, but I can factor out an x. If I factor out the x, it looks like this. Oh shit, is that what it is, Paxton? That might be it. Is there that many students that are potheads?
I have no idea.
It's 4:20 today. I know UC Santa, when I was at Santa Cruz, a lot of students, like, they would organize on campus and just get high on fucking campus. It's crazy.
Yeah, no, my older brother, he lived in Canada and in Colorado, and he's super nonchalant about where he smokes. I don't know. I agree. Crazy.
Now, you may want to, when you're doing logs or natural logs, put a little multiplier sign in here. Because if you don't, the L can suspiciously look like a 1. And then it looks like 31n, and it's not. It only really matters when you've got a coefficient on it. And glancing away for a second made me aware that it looked just like that. That looked like 21n5 and 31n5.
I've been writing my L's in cursive to avoid that. Cause yeah, every time I look up, I'm like, holy shit, is that a 1 or an L? So I've been writing cursive.
That's an excellent idea. I can start doing that. All right, so to finish this off, this is just a number times x. So we would divide by that number normally. If this was like 3x, we would divide by 3. Well, instead, we'll just divide by this crappy looking. Oh, that works better. That works a lot better. Just do cursive on all of it. And we can figure out what that value is. Calculator, oh, calculator. You son of a bitch. Natural log is on or even log is on another tab. I gotta switch back and forth between these two things. 2 times, oop, nope. 3 times. Natural log of 5 plus natural log 8 divided by 2 times natural log of 5. This calculator pain in the ass. I need to bring my actual handheld calculator rather than using a phone app. I'm getting 6.062. The 3 decimal places. Someone else do that on their calculator, make sure you get the same shit. Doesn't look like I need parentheses, but I'm gonna put one in. Yeah, it's still same thing. Oh. That was done with an actual calculator and I got the same thing there. Okay, good. This is why you write notes in your lecture material. Bam. You guys ready for more?
When typing that into the calculator, would you just put 3 then the ln, or would you?
I did 3 times.
Okay. That I was.
Some calculators are okay with just doing 3 and then hitting ln, but
I did it with the parentheses and without a parentheses on the second one, and then I got 2 separate answers. I'm not 6.6. I got 6.6, but that's. I'll try.
see if you guys get the same amount. You should. Because this is notes that I wrote up like 3 years ago with a different calculator. And I still got the same answer. It might be easier to do them one at a time and write down the top and write down the bottom separately. When I put it in my calculator, I did parentheses 3 times natural log parentheses 5 parentheses plus natural log parentheses 8 parentheses parentheses. And then I hit divided by, and I did another parentheses 2 times natural log parentheses 5 minus natural log parentheses 8, and then end parentheses. Or if you do the top and bottom separately, the top is 6.90775 with a few more dots shit. And the bottom was 1.139434. And then you write down a bunch of decimals and then you just divide those two by hand. Not by hand, but in the calculator without having to worry about as much parentheses shit. Sometimes it's easier to just do that.
I did it again and I got 6.65.
Let's see what you did. Did it say it in history? Yeah. Okay. Let's see.
Could be like.
Okay.
And if it's parentheses on the first one.
Yes.
Okay.
What it's doing right now is only dividing the natural log of 8 by 8.
Okay. Okay.
Yeah, you gotta have that parentheses on the top one too. If you don't put the parentheses on the top, it's doing 3 ln of 5, and then it's doing plus natural log of 8 divided by that shit. The 3 ln of 5 is not getting divided. Good?
Yeah.
All right. Hopefully you guys got that. If not, message me after class or something, and maybe you can Zoom with me and show me your calculator. Should have got the same thing. Let's do some more. Let's kick it up a notch. Let's do e to the absolute value of x equals 50. Okay, so here we want to take the logs with the same base, but log base e is the same thing as natural log. Natural log is a shortcut for log base e. So you can take the natural log of both sides. And this brings down absolute value of x. Remember, absolute value yields plus or minus. And this is approximately plus or minus 3.912. Ready for more? Let's go big. Bigger. E to the 4x times e to the x minus 1 equals 5e. Now, it may not be intuitive, but if I had 2 squared times 2 cubed, this is 2 to the 2 plus 3. We could see that if we wrote it out. Same thing's happening here. My base is now e though, so instead, this becomes e to the 4x plus the x minus 1. So this is really e to the 5x minus 1. You still have an issue. I can't do anything with that other e as it is. I don't really want to take the natural log of both sides yet, because the 5 is kind of fucking things up, but I suppose I could. This just gets a little bit easier if we divide both sides by e. Which helps bring up another little reminder thing. If I have like x to the 5th over x, this is just x to the 5th minus 1. We subtract when we're dividing like that. Subtract exponents when you're dividing. Well, this exponent is a 1, even though it doesn't show it. So I could make this e to the 5x minus 1, then minus that 1 on bottom. And the right side is just 5. These cancel out. So now I have e to the 5x minus 2 equals 5. And now I'm in a good position to take the natural log of both sides. I'm choosing natural log specifically because it fills the e. Natural log of e, after I bring the exponent down, natural log of E is 1. That equals 1. So all I have is 5x minus 2 equals natural log of 5. And now I'm just solving x for x the way we already know how. I will add 2 to both sides. And I get 5x equals 2 plus the natural log of 5. And when I divide by 5, I get x equals 2 plus the natural log of 5 divided by 5. If you put that in a calculator, that's approximately 0.722. I say approximately because I'm rounding. Anytime you round, you shouldn't have an equal sign anymore because it's not technically equal. You want more fun? I don't know if you guys can handle the fun. Where's my? It's not my first stage. There's my first stage. All right, let's take it up a notch because that's what we do in here. E to the 2x minus 6e to the x plus 5 equals 0. It's important to recognize that e to the 2x is the same thing as e to the x squared. So I'm going to rewrite that as that. This looks a lot like u squared minus 6u plus 5 equals 0. If I say u equals e to the x. So we could solve this like we normally do. This would be u minus 5 times u minus 1 equals 0. We use our 0 property rule. U equals 5 when we're done, and u equals 1 when we're done. I'm skipping some steps there. U minus 5 equals 0, u minus 1 equals 0, and then we solve for u. But we didn't start with u, so we're not going to end with u. We're going to put e to the x back in. We can now do that operation where we take the natural log or natural log, in this case, of both sides. If I do natural log of e to the x equals natural log of 5. or natural log e to the x equals natural log 1. And we pull the exponent down. The sooner you memorize this equals 1, the happier easier you're gonna find this whole section. Easier you're gonna find calculus. Lots of things get quicker if you start remembering natural log of e is just 1. So this says x equals natural log of 5, or x equals natural log of 1. Natural log of 1 actually has a value too. A simple value, one I don't need a calculator for. 1 you might be able to see from right here. What do I have to raise e to end up with a 1? 0. This one has to be x equals 0. And just so happens that natural log of 1 is 0. So we have x equals 0 or natural log of 5. You guys want to try one? Yeah, this is a little tricky. 4.6 is actually a shorter second. It's just on applications with this shit. So we'll just look at actual word problems. There's one idea about when you're try out. Does anyone need this up longer before I start yanking it? All right. Why don't you guys give it a try? E to the 2x plus 6 e to the x plus 8 equals 0. And we'll do it together as a group a little bit. All these fun examples, Newton's law of cooling. Exponential growth and decay, doubling time, half-life. Hell yeah. Hell yeah, baby. Carbon dating. What? You want still going? You want need longer? What happens here? All right, bring the exponent down. And I get x equals natural log of -2 or natural log of -4. What happens if you do either one of those answers? It's a domain error. Remember, for exponents, if we look at the exponential graph, e to the x goes like this. Y is greater than or 0 everywhere. There is no way to get a -2. No way to get a -4. If we look at the natural log function, it goes like this. And there are no negative values for x. So in both cases, it's no matter how we look at it, there's no solution to this. I was tricky. In fact, and I wouldn't expect anyone to notice it because I didn't think about it when I was looking at it. If you look at the original function that we were trying to solve, this is always positive, this is always positive, and this is always positive. If I add 3 positive numbers together, no matter what I stick in for x, these are always positive. They're not even 0, they're just positive. There's no way to add 3 positive numbers and end up with a 0. One of them has got to be negative to get back down to 0. And we don't have it there, so 3 positives can't equal 0. But I wouldn't expect anyone to know that, but you should always check these and make sure that they work, or write an approximate answer. Leaving it in the natural log is the best way for a precise answer. If you go into engineering and shit like that, though, you won't do that. You need numbers. Because you can't measure natural log of 3 inches. It's not a thing. You need that, you need a decimal value. All right, you guys ready for more? Are we having fun yet? We are having fun, aren't we? This is just like I'm gonna write home and tell my mom all about it. All right, let's change it up. We've been dealing with exponential functions. Let's start working with some natural log functions or log functions. The same way we started with e to the x equals like a, and we took natural log of both sides to get rid of that. This is a side note. We can do the same thing here, but instead of doing it the way we have it, we need natural log of something equals a. And we can raise both sides, treat those both sides as an exponent. So if x equals y is the same thing as b to the x equals b to the y. These are interchangeable. Don't want to do it yet though, because I've got a 4 in front of the x. You can have a couple options. You could use that 4 and put it back up above the x as an exponent. But I don't recommend doing that. I would just divide both sides by the 4. If I divide both sides by 4, I get natural log of x equals 9. And now I can treat both of these as exponents to e. I'm choosing e because, and we looked at this on Tuesday as a reminder. A to the log a of x is just x. This fell out. It was one of the last things we did on Thursday or Tuesday. Well, ln is log base e. So this would apply to log e to the ln of x equals x. So if I do that, I get x equals e to the 9th, which is a really, really large number. Those are all properties we took advantage of. I think we can squeeze in another one right here. We're gonna do the same thing here, but now we're gonna use the base that's present. We're gonna raise both sides, treat both sides as an exponent of 3. And 3, the first power is just 3. 3 to the log 3 cancels out, and we're just left with x cubed minus 5 on the left. That's just something you're going to have to memorize. This is not intuitive. Hell, nothing with natural or logs is intuitive, is it? Not really something like you may get, you'll eventually get comfortable working with them. But log 2 doesn't mean fucking anything to me. Log 2 means less to me than square root of 2 means to me. Square root of 2 I know is like 1.3, 1.4-ish. Log 2, I have to fucking get out a calculator. I have no idea what log 2 is. But exponent, matching base, they cancel out. You get what's inside the argument. Here, solving is easy. We add 5 to both sides. We get x cubed equals 8. We take the cube root of both sides. And we get x equals 2. You can even check. Log base 3 of 2 cubed minus 5. Does that equal 1? We could have done that up here. If you plug in 4 natural log of e to the 9th in a calculator, do you get 36? So there are, when you're solving these, there are some checks you can do. If you're willing to take the time and put it into a calculator to check your work. Ready for some more? Does anyone need that longer? Let's try. It's got super fucking cold.
What's that one side?
Right?
Like 85 degrees.
That's why I didn't wear my jacket. I've worn my jacket a lot longer than I normally do. Quit drinking 3 years ago, and once I quit drinking, like my body temperature just at all times went down. I used to run fucking hot. Didn't matter if it was just even like once a week having alcohol. For some reason, I just run hot the entire fucking week. I quit drinking and then just fucking now if I pull the blanket over me in April, and I'm in sleep. It's crazy. All right, so when we don't see a base in the log, these are base 10. But that's not going to help us right now because we can't really raise them to the same power yet. Well, we could. In fact, it might remind you of what we need to do. But I don't know that's going to help. Well, we'll do it both ways. What is the property where we had addition with logarithms? Does anyone remember? The rule we had before was log x plus log y is log of xy. So multiplication on the inside turns to addition on the outside. This is a two-way street. I can put these back together by multiplying the insides. Now here you can either raise both sides as powers of 10 or recognize that if this is log and this is log with the same base, then these have to match for them to be equal. This always works out because when we don't have a base showing, the base is always 10 if it doesn't show. So now I've got 10 log 10. That cancels out and I'm left with x times 2x plus 1 on the left. On the right, I'm left with x plus 8. Notice I have restrictions inside here. I can't have the inside ever be negative. We saw in the graph of logarithms, the inside's never negative. But by raising it to an exponent like this, I've now made it so these things can be negative. So when you're doing stuff like this, you need to check your answers. Because we have allowed bad answers now. Got rid of the domain restriction. So just solve it like normal and plug it in and see if anything works. And you really don't need a calculator. All you need to do is find out if you make the inside of any logarithm negative. So we'll solve normally. We would do this by distributing. And I'm going to subtract the x plus 8 over at the same time. So subtract over and distribute. When I do that, I got 2x squared minus 8. I can divide by 2, make this a little bit easier. You have a couple approaches here. One approach is saying x squared equals 4 and taking the square root. You get x equals plus or minus 2. The other option you have is factoring that. That is the difference of squares. This also leads to x equals plus or minus 2. That's some old algebra shit we did, but now I'm just looking at different ways of doing it. So plus or minus 2 means x equals 2 or x equals negative 2. I use both of those values in this initial equation? You got to go all the way back up to the top. Let's check it out. If I stick in 2, what do I have as the argument inside the first one? 5. Here I have 2. Here I have 10. None of those are negative. All good. So the x equals 2 works. What about x equals negative 2? This one actually kills every single one of these parentheses. Well, no, it even kills that one because you can't take log of 0 because it can never equal 0 either. X equals negative 2 does not work because it leads to log of negative 2 in the original equation. So takeaway from that is if you clear logs, always check your answers. At this point, it's probably a good idea to always check your answers anyway if you can. You could go through and put this in a calculator and make sure log of 5 plus log of 2 equals log of 10. I already know that it does because log of 5 plus log of 2, doing this multiplication thing. It's 5 times 2 is log of 10. So you get log of 10 on both sides. Ready for more? Are you ready to learn? Yes, I'm ready to learn. So it's already in a log, so what can we do to get rid of the log?
And, basically,
Yeah, so treat both of those as exponents at base 3. Three cubed is 27. It goes in and solve that bad boy. You guys already know how to do this. You're champions at it. Fuck. that factors to 4x plus 13 and x minus 2. Now we gotta check our answers. I think checking x equals 2, you can do it visually quickly. 4 times 2 is 8 plus 1 is 9. This turns into 9 times 3 on the inside. That's a positive number for sure. Remember, all we need is for this thing to be greater than 0. So if I put in negative 13 fourths, here the fours cancel and I got negative 13 plus 1. That's negative 12. I can do negative 13 plus 1 pretty easily. I'm not going to bother figuring out what this is. I know 13 over 4 is bigger than 1 and it's negative. That ends up being a negative number there. So a negative times a negative is a positive value, which is greater than 0. So they both work. Only because I started with the equation in this form. Notice what happens if we started as log base 3 of 4x plus 1 plus log base 3 of x plus 1 equals 3. The first step is putting them together in multiplication to get this. So we're going to get the same x values. But now negative 13 over 4 doesn't work here. Which is fucking crazy. It works here, it doesn't work here. But these are supposed to be the same things. The reason why they're the same thing, the reason why it doesn't work here, doing log xy equals log x plus log y required shifting or required raising both sides as exponents. When we derive the problem or when we derive the rule, we actually did that in lecture notes. We showed how to get it. Which meant doing this introduces potentially bad answers. Which is crazy, because these are literally from what we talked about the same. But you do have to check your work when there's variable stuff. That seems tedious. I'm not gonna do that one. It's just another solving. This one's got a solving, but it's slightly different. ln of e to the ln of x minus ln of x minus 4 equals ln of 5. Now, you can either recognize that e to the ln of x, the e to the ln cancel out, and it just becomes x. Or you can bring the natural log of x down. I think this is the more intuitive way. You have natural log of x times natural log of e now. Minus natural log of x minus 4 equals natural log of 5. Because the ln of x is an exponent, and we can bring down exponents. ln of e is 1 though. So this turns into ln of x minus ln of x minus 4 equals ln of 5. You know, it's kind of funny, if we have a couple options. If I convert this as is, this becomes ln of x over x minus 4 equals ln of 5. Or we can do this. Add the ln of x minus 4 to the other side. And we get ln of x equals ln of x minus 4 plus ln of 5. And when we put those together, we have this. I think you're less likely to make mistakes doing it the way on the right. Because it sucks having fractions when you can avoid it. No fractions this way. All right, so we can raise both the sides to the e power, and we get x equals 5x minus 20. The other way is recognizing that these are both natural logs, and for them to be equal, the insides have to be equal. So if I solve this, I get 20 equals 4x, x equals 5. You should check your work on this. But it should work. Ready to look at some applications? This is the good shit. This is the, why the hell are we doing this, Jones? Could I possibly give a shit about doing this for? Well, let's talk about it. 4.6 is applications and models. When we have exponentials, this is called the exponential growth or decay models. Things that exponentially grow include things like population, interest in finance. Has exponential growth. That's most of them. It's the most common ones. I'm sure there's other ones. Exponential decay. Here you've got things like carbon dating. Or radioactive decay. That's how carbon dating is done. It's the decay of the isotopes of carbon. The Newton's law of cooling. Heat dissipates at an exponential decay model. Where it happens, if we're both looking at e to the x, or a to the x, or something like that, or a to the x. As long as x is greater than 0, we have exponential growth. As long as x is less than 0, we have exponential decay. So this would be given to you as e to the negative x. They wouldn't just say use negative numbers for x. You would have it in the form a to the negative x or e to the negative x. The basic one, most basic form of it, it doesn't show you one way or the other what it is. It's y equals y naught e to the kt, where k is constant. And y naught is the value at t equals 0. In fact, that's why they call it y naught, because then you'll notice if we plug in 0 for t, we have e to the 0. And anything to the 0 power is 1. Sometimes you don't know what the decay constant or the growth constant is. So let's look at an example where you have to find it. Let's say we have a chart where we have in years, and this is carbon dioxide in parts per million. Or this is atmospheric carbon dioxide. Where does this come up? Global warming. They attribute higher temperatures going up due to more carbon dioxide in the air. Too many fucking mouth breathers on the planet generating carbon dioxide. We could save the planet if we just killed off all the stupid people. That's my pro choice. If I'm president, if I'm emperor, I don't know. Stupid people's kind of hard to, where you tag the line and stupid people. All right, enough craziness. Let's put some examples in. One way to find the growth model, because global warming is going to have it growing, is just pick 2 years. And calculate K. I strongly suspect K changes as the population changes. Not just the population changes, but we introduce more technology. This is assuming like it's just based on population. But we also are introducing more stuff that produces carbon dioxide, like vehicles and shit like that. So like let's go with 2070 or 2020, 2175. And we are going to do y equals y naught e to the kt. Let's treat t equals 0 as our lowest time. Or effectively year 2000 here. With the setup I chose to choose. If I chose 1990, it'd be 1990. How much time has passed between 2000 and 2175? 175 years, right? So t equals 2175 minus 2000 is 175 years. I have carbon dioxide level at t equals 0. And I have a carbon dioxide at t equals 175. So I know what the right value or the both sides are. The only thing I don't know here is K. Oops, I'm plugging the wrong values. The 1090 is the carbon dioxide. The 375 is the initial one. And I have e to the k times 175. We want to find k, so we need to get e by itself. We divide both sides by the 375. We pick the natural log of both sides to get rid of the e. I'm going to get k equals natural log of 1090 over 375 divided by 175. What does that equal? K equals 0.006097. At this point, when you have something like that, when you're using it in science, you're gonna use it to make predictions of the future. So like, let's say, I don't even know if this is true, but it's written in this problem I got right down. Pre-industrial levels of carbon dioxide were 280 parts per million. When will we hit 3 times that? Well, first thing we need to know is what is 3 times 280? 280 times 3 is 840. That's going to be my ending Y. K equals 0.006097 was developed using T0 is 2000. So we're going to use that same idea here. So Y0 will be the 375 that we had before. And now this is our target Y, 840 equals 375 E to the 0.006097 T. So we solve it like we do the other one. Instead of solving for K now, though, we're solving for T. We can divide both sides by that 375. I recommend keeping K stored in your calculator. Calculator and not using this rounded value. But I gotta write something down. And so what do we do here? We take the natural log of both sides. And I get natural log of 840 over 375 equals 0.006097 T. So we both divide both sides by that super awesome decimal. And we get T. $840 divided by 375 divided by answer. There we go. I'm getting T equals 132.27, blah, 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 blah. We're looking at years, so I don't need the decimal place at all for the years. I'm just gonna say T was 132 years. That wasn't what it asked us though. It asked us when we will hit that.
Here,
This is the T added to T naught. So T naught plus T, 2000 plus 132 is the year 2132. Does that kind of track with what we had on the table before? 2175 said it hit 1090. So it should have hit 840 before that. That makes sense. That works. The same kind of thing works with doubling time or finances. When you're working with finances, a lot of times you might want to know how long it takes to double your money. At continuously compounded interest. Follows the same formula, y equals y naught e to the kt. When they say it in finance or business, they tend to say PE to the RT. But the K is just the same thing as an R, and the P is a Y naught, and the A is a Y. They just use different letters, but it means the same thing. Yeah,
so if you you can use those interchangeably,
yes,
because I knew it as a.
we tend to use that only with finance though, because P is principal. So, finding doubling time. Is actually kind of neat. I'm not even going to give you an interest rate. If I start with P, what do I have when I've doubled my money? I have 2P, right? I start with P. If I start, not strat. Double means 2P. Look what happens. We're just looking about the multiplier, dividing by P. Doesn't matter what we fucking start with. It's irrelevant. The P goes away. And when we take the natural log of both sides, we got natural log of 2 equals RT. Where T equals the natural log of 2 over R. Now, I don't recommend memorizing that. It's enough to memorize the growth and decay model the whole way. How does this change if I want to go for triple my money? If I go for triple, I have 3P. And the P still divides away. And if T equals ln of 3 over R. What you end up getting if you just solve it in the generic form is T equals the natural log of the multiplier that you're looking for. Divided by the rate. So if you want to make 10 times your money and you're using compounded interest and you know the interest rate isn't going to change. It's kind of neat. The same thing works for population models, kind of like the carbon dioxide one. Population goes up, do the same setup. We should look at exponential decay before we're done though. So a common thing we care about in exponential decay is half-life. We want to know how long it takes for something the radioactive decay to cut in half. For radioactive elements. It's a very popular one of this. So let's say we started with 800 grams. And after T equals 2.5 years, our ending value is 400 grams. It's the half-life. So this is the half-life. Half-life is the number of years it takes to cut a value in half. Number of years for the amount of an element to be half. By decay. Radioactive elements, they're not stable. They have either, I don't remember, extra electrons or not enough electrons. So eventually shit changes. They either pick up electrons or they shed their extra electrons and they revert to a stable non-radioactive version of it. But it takes time. And so let's say we had 800, we got down to 400 in 2.5 years. We wanted to find create a decay model for this element or this substance. So we've got our y equals y naught e to the kt. Or if you like a equals p e to the rt, use it, it's fine. Y is the ending value is 400. Y naught was the starting value was 800. And we have e to the k times 2.5.
What, because it was decay, it would
It's going to end up being negative when we do it. We divide both sides by 800. And we get 1/2 on the left. We do the natural log of both sides. Natural log of 1/2 is natural log of 1 minus natural log of 2. And natural log of 1 is 0. So this is the same thing as negative natural log of 2 equals 2.5k. These are identical. But you're probably going to put it in a calculator anyways. But here you can see where the negative comes from. Divided by 2.5. And we get k equals ln 1/2 over 2.5. Or negative ln of 2 over 2.5. Fun shit is, what if I didn't tell you how much it started with? What if I started with P? Finding half-life, the final amount is 1/2 P. So we have 1/2 P equals P e to the KT. Didn't really matter what we started with, as long as we're looking for a time, a multiplier. So this is just ends up being the exact same thing as what we just looked at. T equals the natural log of the multiplier over R. When you're looking for time and you're looking for a specific multiplier, like doubling or tripling or half-life, something like that, it's the same thing every time. Here we weren't looking for time, we were looking for k, but the process was still the same. The k was in the exponent just like t was. So it falls out the same way. The only one that's really different than those is the law of cooling. Law of cooling. So the temperature, let's say I call it F of T, equals P naught plus CE to the negative KT. And C and K are constants. This also applies to warming. K would be positive, you'd end up with a positive exponent rather than a negative one. And you'll see stuff like this when you take physics. We're running out of time. I don't want to hold you guys any longer. You'll see this in physics. I don't think there's anything in the homework with things about cooling. If there is, I'll take it out. Or I'll get full credit on it. It's more tedious. Because now you have two things you don't know, C and K. Look out. So I'll sit here for. That's a wrap, folks.